You have seen that the determinant of a matrix can be calculated using a cofactor expansion. You have also seen how convenient it is to have zeros in the matrix. In this video, I will show you that you can use row operations to create more zeros. Let me first stress that some of the row operations change the value of the determinant, so you have to be very careful. We start with a 2 by 2 determinant. What happens when we apply one of the three row operations? If you interchange the two rows, the determinant gains a minus sign. If you multiply one of the rows by a constant k, the determinant is multiplied by that same constant. Note that the constant k should be non-zero. For the determinant, a k of 0 is okay. However, multiplying a row by 0 is not a valid row operation. A row operation has to be reversible. You can use this property as follows. If a row has a common factor, you can pull that common factor out of the determinant, and a 3 is pulled out of the first row and an 11 out of the second row. The elements of the determinant are now smaller and easier to handle. A consequence of this property is also that the determinant of k times a 2 by 2 matrix A is k squared times the determinant of A, because A has two rows with common factors k. Finally, you can add a multiple of a row to another row. The terms plus AKB and minus BKA cancel, so the determinant does not change. Here's an example of the use of this row operation. Determinants are special in the sense that you can manipulate the columns in exactly the way as the rows. Remember the transpose of a matrix? The rows of A become the columns of A transpose, and vice versa. For a 2 by 2 matrix, just elements B and C are interchanged. The determinants of A and A transpose are the same. That has neat consequences. In a determinant, you can treat rows and columns in exactly the same way. If you interchange the two columns, the determinant gets a minus sign. If you multiply a column by a non-zero constant k, the determinant is scaled by that factor k. And if you add a multiple of a column to another column, the determinant does not change. Beware, these operations on the columns can only be used in determinants. Do not use column operations elsewhere. For example, when you are solving a system of equations or when you are calculating an inverse matrix. There, rows and columns should be treated differently. All this is for 2 by 2 determinants. Can we use the same operations on larger determinants? Luckily, we can. Each of the three operations changes just one or at most two rows or columns. So there are at least n minus 2 rows or columns that stay the same. Then we can take the cofactor expansions only across the rows or columns that have not changed. For example, this matrix B is the same as matrix A, only its columns 1 and 3 have been interchanged. What about the determinants? The second column stays unchanged, so we can expand both determinants across that column. The expansions have exactly the same weights, minus b, plus e, and minus h. The differences between the two expansions are in the 2 by 2 determinants only. 2 by 2 determinants behave according to the rules that we have just derived. So also this 3 by 3 determinant of b is minus the determinant of a. This example can be generalized, and we can conclude that the same rules are valid for all n by n determinants. Finally, an example of how these rules can simplify calculations. Suppose you want to calculate this determinant. Of course, this can be done in infinitely many ways. I'll show you just one of them. First, I don't like to work with fractions, so I'll take out the factor of 1/10 in the third row. The 1/10 becomes a factor before the determinant, and the third row of the determinant is multiplied by 10. Then I'd like to take advantage of the two zeros in the first row. I'll reduce the 6 in the top row to 0 as well. Therefore, I subtract the 3 times the first column from the last column. The value of the determinant stays the same. Now I'll expand across the first row into just one 3 by 3 determinant. Next, I'd like to make the numbers of the first column smaller. That can be done, for example, by row addition. Okay, that's better. Now what? Well, maybe now reduce to echelon form. I'll start with clearing the first column. Again, I want to avoid fractions, so I'll use the 1 in the first column to reduce the -7 to 0. This is the result. I could expand this determinant across the first column. However, I'd like to show a row exchange as well, so I'll continue to reduce this to echelon form. I'll reduce the -2 in the third row to 0 by adding the first row. If I then interchange the first 2 rows, the matrix is in echelon form. So I'll do 2 row operations in the same step. Note the extra minus sign because of the row exchange. The determinant of this triangular matrix is the product of its diagonal elements, and we end up with this number. So you may simplify the calculation of a determinant by row and column reduction. Just keep track of the changes when interchanging rows or columns and when pulling out a common factor. And as always in practice, most matrices are not this small and do not have such nice integer elements of roughly the same size. So later on you'll use a computer to calculate your determinants. However, you should understand the principles of what a computer does for you.